Alrighty, hello everybody, and thank you for being here this morning. We are going to talk about infrared spectroscopy today. Last week, I took you into the hallway and I showed you what the instrument looked like, and we saw it. We're not going to get to use it this semester. Maybe next semester you will, but we are going to learn about the theory and the principles behind infrared spectroscopy. What is it? How does it work? Um, let's just get to it. All right, so spectroscopy. It is a technique where we take light. Light is electromagnetic radiation. We take a photon of light, photons of light, we shine it on some matter, and something happens. We are all born with two natural spectroscopic instruments in our face. We call them eyeballs. Vision is the way that we detect it. We can only see visible light. Visible light is between 400 to 700 nanometers. That was one of your pre-lab quiz questions. 400 to 700 nanometers. Roy G. Vib, the rainbow, right? Roy G. Vib is the mnemonic red, orange, yellow. Roy, R-O-Y, red, orange, yellow. B, Roy G. Vib, green, violet, indigo, etc., etc. So that is the rainbow colors. That is only a very small amount of the entire electromagnetic spectrum. There's significantly longer wavelengths. There's significantly shorter wavelengths. We can only see the ones from 400 to 700 nanometers. I know mosquitoes can see some in the infrared. Some birds and some bees can see in ultraviolet light. It depends on your own instruments. So a little bit below red, right? Red is considered to have a longer wavelength than blue. When you have a long wavelength, the wave goes up and down a lot less frequently than a shorter wavelength, which goes up and down a lot more frequently. And so we say that waves with longer wavelengths like red have lower energy. Wave with shorter wavelengths have higher energy. If you have a shorter wavelength, you have a high frequency because when you're a short wavelength, I mean, consider the wave over here, right? If this is a very short wavelength, you're going up and down very frequently. Whereas if you have a long wavelength, you're barely touching the top and the bottom of your amplitudes. So short wavelengths have higher frequency and therefore they have higher energies. Longer wavelengths have lower frequencies, they have lower energies. There should be some review from 111A from some physics. And below red, we have infrared. Infra means below in Latin. And above violet, we have ultraviolet. Ultra means beyond in Latin. So immediately to the left and to the right of visible light, which is what we can see, we have infrared radiation and we have ultraviolet light. Infrared radiation, you can feel that as heat. If you guys have ever been to Universal Studios and you've seen that show with the exploding plane and everything, or if you've just been next to an explosion safely, when you see the fireball, you can feel the heat on your face. That heat that you're feeling is infrared light, infrared radiation hitting your skin. You can feel ultraviolet light when you go out in the sun at Long Beach and you forget to wear your sunscreen and your skin gets cooked and crisped and charred. So that is ultraviolet light, very high energy light hitting your skin. That's why you get cooked. Um, if you have any higher energy than that, you get what's called X-rays, and we know that X-rays can see through our skin. It can see the bones. The guy who discovered it was actually working in his room. He had a very powerful light bulb, and he turned it on, and he noticed he could see the bones inside his hand, and he was like, "Whoa, there's something going on in here." So yeah, he was dousing himself in a bunch of X-rays when he discovered it. But he lived a little bit longer, I think. But of course, they're dangerous because they're very high energy wave. That's why your doctor or dentist is like, "Okay, everything's safe. Don't worry about it." And then they run all the way to Ohio and they press the button. So yeah, they're safe in minute doses, but they're not safe at all in general. They're very high energy particles. Then you have gamma rays. That is what makes Superman Superman. The gamma rays from the sun's radiation interact with the cells of Superman and give him all those superpowers. I think Hulk does the same thing, but in real life, gamma rays are just going to kill you. They'll vaporize you, they'll fry you on the spot. There are some theories that some mass extinction events in our Earth's history were probably caused by gamma ray bursts from a nearby star that went supernova. And basically, it just fried all of the animals on the planet. And that's why 99% of the population on Earth died. So, again, Very dangerous gamma rays. And of course, anything stronger than that is just called the cosmic ray. This is what comes out of the black holes. So, you're ripping reality at the very fabric. So you're creating very high energy particles, very high energy waves. On the lower end, we have again infrared. We also have like longer wavelength infrared lights. We call those microwaves. We use that to cook our food. So just like the X-ray guy, the guy who discovered microwaves back in the 1950s, he was working with a device that emitted radiation, and he found out that whenever he was working with it, that the chocolate that he had in his pocket was melting. So he's like, well, there's something going on in here, right? So he was cooking himself, unfortunately, but he figured it out, and now you get to enjoy your popcorn and your ramen and all that stuff. So we have microwaves, very low energy, long wavelength radiation, still high enough energy to shake up the water, heat up your food. And then we have radio light. I know radio is usually associated with hearing, but radio waves are a form of photons that just have low energy. So radio waves are light. It is also part of the electromagnetic spectrum. And these are so long, they could be a mile, they could be like 2 miles, 10 miles, 100 miles. That's why you have AM radio. You can listen to AM radio like hundreds of miles away from the station. You can listen to FM until you go up. I forgot you guys are in Long Beach, but yeah, here once we go up the Grapevine in the mountains, you lose all radio signal and you start getting the LA radio stations. So depending on the length of the radio wave, you can have a long distance, long range, or a low distance. We also use it for NMR, we use them for MRI, and Wi-Fi. Wi-Fi is a radio wave. Wi-Fi is in the radio wave range, and you saw recently that the government can actually use Wi-Fi signals and use your modem like an eyeball. They bounce around the house, and when they bounce back, they can detect them. And depending on how much time it takes, they use it kind of like a sonar, and they can find out who's in the room, how many people are in the room, and supposedly they can find out with 80% certainty who is in the room, like the identity of the person. So the conspiracy theorists were right. They can spy on you through your Wi-Fi, but it's all radio waves, right? So just get a radio jammer. You're safe. But anyway, the point is, it's a very large spectrum. There's a lot of different energies, a lot of different wavelengths. We can only see visible light. Very unfortunate. There's probably beings of X-rays all around us, and we just can't even see them, right? Who knows? Maybe somebody in a black hole has eyeballs that can see gamma rays. That would be interesting. And all of these are photons. All of this is light. X-ray is light. Gamma ray is light. Radio wave is light. Microwaves are light. All of these can be described by the equations below. The speed of light is equal to the wavelength times the frequency of the wave. Or we can say the energy is equal to Planck's constant times the frequency. And of course, if we solve for frequency, it's just hc over lambda. This symbol lambda means wavelength. And in physics formulas, we usually measure that in meters. So make sure you know your units as well. We use nanometers for visible light because, well, it's within those nanometers, so it's always nanometers, right? Infrared goes from 780 nanometers to 1 millimeter, right? It's a little bit longer than red, but shorter than microwaves. Not excessively long. It's not like a kilometer long. That's a radio wave, you know? So you don't really need to know these formulas. They're kind of more like review for your reference, but this is just the foundation of the electromagnetic spectrum. Are there any questions so far? Okay, so we move on to the next slide. Depending on what sort of wavelength you're using, depends what kind of interaction you get with matter. So radio waves, when you shoot them in a magnetic field to a compound under liquid nitrogen, you get signals from the hydrogen atoms themselves. So you can actually use NMR and radio waves to find out how many hydrogens are attached to a carbon. Is it a CH3? Is it a CH2? Is it an OH? So radio waves are specifically for hydrogens and their environments. Infrared is for functional groups. So that was also one of your pre-lab quiz questions. What information can we get from IR? Functional groups. We don't know anything about molar mass. We don't know anything about molecular formula. We just know what functional groups are present based on their IR signals. And we will explain that more in depth throughout the rest of the lecture. There's also UV-vis spectroscopy, where you can use visible light and ultraviolet light to do analysis. So for example, we all have a visible spectroscope in our face, right? The eyeball. So when you look at a carrot, it's orange because it has carotene, and carotene absorbs and reflects a wavelength in the orange visible light spectrum. So everything that we see, everything that we look around, all that has color is UV vis, pretty much. Everything that we detect is absorbing a photon of energy from the sun and then either reflecting it, diffracting it, or scattering it, and then we interpret that as color. So colors directly come from electromagnetic radiation, right? Go figure. And of course, we also have X-ray crystallography. I took a class last semester where you can take a compound and shoot X-rays at it, and it'll diffract the X-rays in such a way that you can calculate where the atoms actually are next to each other, and you can calculate how long, very precisely, how long is the actual bond. So this is how we found out how the structures of molecules actually look like. There's microwave reactors for organic synthesis. All they do is heat up your reaction to make it go faster, right? Because they're lower energy. They're not going to do very much. So we also have like ionizing radiation, radiation that is so powerful that all of the electrons are stripped away from the atom. So it really does depend, right? In this case, we're just focusing on infrared. What does IR stand for? Infrared radiation. Okay? This tells you about the functional groups in the molecule. Are we okay so far? And again, if you have questions, feel free to put them in the chat. Feel free to unmute and say, I have a question. This is the only lecture we get for IR, so the time for questions is this lecture right here. Alrighty? So what do I mean by absorption? What do I mean by emission? If you might remember from 111A, 111B, we talked about energy levels in the atom. We talked about N equals 1, N equals 2, right? We have like N equals 1, and then we have like N equals 2. And then we can have an electron that goes up from N equals 1 to N equals 2, and then it relaxes and goes back down. And if it goes up, we call it absorption. And if it goes down, we call it emission. You might remember. And so this is all quantum physics, quantum mechanics. We call it quantum because it has a specific number, a specific quanta. So for example, imagine that you want to go buy, I don't know, a car and it's $5,000, but you only have $3,000. You can't buy the car. Now you have $4,000. You still can't buy the car. Now you have 5,000. Now you can buy the car. Well, what if you had 5,500 or what if you had 6,000? Well, you can buy still only one car and now you'll have some left over, but you still only have one car, right? Energies, atomic energies work very similarly. There's only a specific amount that you need. Anything lower and the electron is not going to jump. Anything higher and all of that excess energy is just going to be left over. It only absorbs a specific amount of energy, and that is why we can take a photon of a specific amount of energy and shine it at a compound, and depending on what type of bond it is, depending on what functional group it is, it'll absorb it and then it'll re-emit it, and we can measure that in the instrument. So it's unique, is what I'm trying to say. All of these absorptions are unique depending on the type of the molecule. And they are unique because it takes a very specific amount of energy, no less and no more. Only that amount of energy will cause that action to happen. Just like you could only purchase what you want when you have exactly the right amount of money from a store. Obviously, if you're one of those barterers people who are like, oh, come on, bring a lower price, whatever, sure. But it's an analogy, right? The point is that it has an exact amount of energy that it takes to create an absorption or an emission. And of course, the larger the energy, the higher the energy. So that is when you can absorb something with like ultraviolet. Sometimes you shine an ultraviolet light at highlighter colors and they glow. That's because it's absorbing the light and re-emitting it. And then you also have the glow in the dark lights, right? The plastics, you put them in regular light, you turn off the lights and they're glowing green for a while. That is another form of absorption and re-emission. We call that phosphorescence. When you shine the UV light, we call that fluorescence. Similar processes, they both involve absorbing and re-emitting, but just with different timelines. So this is just how matter works. Again, if you're looking at anything right now, like the color blue, well, guess what? It's absorbing the energy and re-emitting only the blue energy. So that's why we see the blue, right? And we do have spectroscopes, right? If you have a piece of bread and you know it's supposed to be white bread, and suddenly you see something green in the white bread, you know that something changed, right? The green color is indicating a change. Most likely it's getting moldy. So we do use this information to make decisions about our world. And so we use this information in IR to make guesses or to determine what functional groups are present in our molecule. So higher energy obviously would be for higher energy processes like electron excitations. Infrared has lower energy, lower than red, infra, right? So it's not going to cause electron excitations. It is going to cause bond vibrations. And we'll talk about that a little bit more. But does this make sense? The concept of absorption and emission? It happens at a very specific amount of energy. And so we can measure that energy and we can see, okay, this is a OH vibration energy. This is a CN vibration energy. So why do we use IR? Again, it just have you guys ever seen the opera singers? You know, the like a really high pitched alto soprano opera singer, and they're singing and they break the glass. Well, that's because the glass has a specific frequency that it will vibrate at. And when you match the sound wave frequency to that glass frequency, the whole thing is gonna violently shake because they're at the same frequency and it's gonna completely explode. So in theory, somebody could make a gun that has the same frequency as a human being, and they could just literally make someone explode by shooting them with the right frequency of energy. Pretty scary. I think that's one of the bases of the heart attack gun that the FBI was working on back in the 80s, but you guys can look that up on your own. The point is resonance. That's what we call that. Resonance. When you have two energies that are resonating, the energy gets amplified, and that's what we observe as the vibration of the molecule. It just so happens that the vibrations of the molecules happen to have the same energy as the vibrations of an infrared photon. That's why we use IR. And so in order to use IR, we have to consider something about the bond. First of all, the bond has to have two separate atoms. So for example, if it's H2, you have H and H, there's no polarity, you don't see it in IR. So one of your pre-lab quiz questions was true or false. All compounds are IR active. False. If it is a symmetrically stretching molecule that cancels out its dipoles, or it doesn't have any at all, you're not going to see it in IR at all. So some molecules are invisible to IR spectroscopy. Not all molecules are IR active. So you need a polar bond. So carbon, oxygen, that's a polar bond. Iodine, chlorine, nitrogen, hydrogen, carbon, hydrogen, oxygen, oxygen, it's the same one. There's no polarity, so you don't see that either. And the more polar the bond, the stronger the bond, so the more energy it's going to take to vibrate it. Are we clear with that? There needs to be a dipole change in the molecule of a heteronuclear bond, that means different atoms, in order to see an IR signal. Any questions about that? And that is why functional groups are the things that stand out the most, because functional groups are made out of multiple atoms of different polarities, right? Carboxylic acid, CO, oxygens, alcohols, oxygen, hydrogens, right? Esters, carbon, oxygen, oxygen. Ethers, carbon, oxygen, carbon. Amines, nitrogen, hydrogen, right? Those are all different atoms. They are heteronuclear and they are polar, so you see them in IR. We'll see more examples pretty soon. So any questions about this concept? More polar molecules, more polar bonds are stronger, so they take more energy to vibrate. So in IR, we use what's called the spring model, right? So I have a spiral notebook with me right here. You can see this is kind of like a spring, sort of. And you know, the spring is very flexible, so I can like bend it and wag it. And of course, if the paper wasn't on here, I could just stretch it out and distort it. So you could think of the bond between two atoms as a spring, and it can wiggle and it can vibrate and compress and stretch. And sometimes you can have them be the same weight, like if you have a carbon-carbon bond, well, that would be like having two masses on opposite sides, the same mass, and they can only vibrate in a specific intensity at a specific frequency. But maybe you have something like HCl. I mean, the molar mass of chlorine is 35. The molar mass of hydrogen is 1. So, I mean, that's almost like a paddle ball, right? You have like a really heavy molecule vibrating with a really light, a very heavy atom vibrating with a really light atom. And so you get a very intense signal. You get a lot of springiness. That is why you see a stronger signal in your IR. So the point I'm trying to make here is that we look at the spring model kit and the spring model of the atom of the bond. And that is what we use to base our frequency vibrations of the IR spectrum. We start from a low energy and we scan all the way to a high energy and we measure all of the absorptions that happen. And then depending on where the absorptions are, that's going to tell us if it is an OH bond, if it is a CN bond, if it is an NH bond, if it is a CO double bond, etc., etc. So the bonds depend on the different sizes of the atoms, the polarities, and also the way that they symmetrically or asymmetrically stretch. It's a lot, but you'll see it as we get through it. And I'm also going to show you some animations too. I'm not just going to not show you things moving. I'm telling you things are moving. I'm going to show you how they move. Okay? So any questions about this so far? Okay. Moving on to the next slide. So I showed you the IR spectrometer. It's very small. Looks like a little toy microwave. You put your sample in the little glass sensor, you sandwich it down, and you get your IR spectra in the computer. So first and foremost, I want to say that spectrum is singular. Spectra is plural. So this is one, and this is two or more. So if I give you one graph, this is a spectrum right here. This is a spectrum down here. When I say spectrum or spectra, I'm talking about this graph. Not this specific one, but like something that might look like this. Notice on the x-axis, we have something called wave number, right? That's over here in the third point. Wave number, that's just mu with the bar on the top. The units are in centimeters inverse or inverse centimeters, 1/centimeters. Why? I don't know, man. When they invented this, they used it. They thought it was convenient. Everybody accepted it, so we continue to use it, right? Remember that the units of any formula and the speed of light are in meters, right? So the speed of light is recorded in meters per second. So if you're ever converting from wave number to energy, you have to convert from centimeters to meters before you get a right answer. Otherwise, you're going to be off by a few magnitudes of 10. So just to be aware, in infrared spectroscopy, we specifically use wave number for our IR x-axis, wave number. You can also call them inverse centimeters if you like. It depends on the chemist. This is on our x-axis. And notice that there's no zero. It actually goes from high to low, from 4,000 to 400. But a low wave number has low energy, and a high wave number has high energy, right? So right here, 4,000, this is high energy. And then over here, this is low energy. That's pretty intuitive, right? Small number, small something, big number, big something, right? So if you have a small number, you have small wave number energy, big number, big wave number energy, right? The number itself tells you if the energy is high or low. And you know how to count, I hope. So you should know that 1 is less than 2, 3 is more than 2, blah, 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 blah. 4,000 is bigger than 500, right? So if I tell you high wave number, you should think to yourself high energy. Low wave number, low energy. And remember that wave numbers are special. That's why we put the bar over the frequency. The units are in centimeters to the -1. You could also see that here on the x-axis. On the y-axis is transmittance. Think about the word, to transmit, to go through, right? I transmitted the signal. We have an IR photon being transmitted from the instrument to the detector. If it goes through 100%, there's nothing there, nothing absorbed it, nothing interacted with it. So it goes through. The transmittance should be 100%. As soon as it gets absorbed by anything, like a polar bond, the transmittance is going to go down, right? Low transmission, high absorption. So when the absorption is high, your transmission is low, and that's why you see these very low-hanging peaks right here. So the lower hanging the peak, the higher the absorption, the more intense the absorption. Make sense? Sometimes you might see some IRs that instead of percent transmittance, they'll say absorbance. It'll just be upside down. That's why the one that we saw in the hallway last week was upside down, because they weren't using percent transmittance on the y-axis, they were using absorbance. They'll both still show up at the same x value, and they will still both look the same. They're just going to be flipped. So regardless of what it is, you still need to be able to identify the information based on the wave number and other factors which we will talk about. And again, just be aware our general range is from 4,000 wave numbers to 400 wave numbers. High energy to low energy. Any questions about this? So this is what we are learning to read. We're learning to read the spectrum. And based on the peaks and their wave numbers and their shape and intensity, we're going to find out what they are. Okay. So I'm going to clear the drawings, move on to the next slide. All right. So again, this is the physics equation behind the spring model. We call it the harmonic oscillator. Uh, you take a spring, you put two atoms in between, and they vibrate. You can plug in the molar masses in the reduced mass equation. So if you have like oxygen and carbon, you would plug in 14 and 12, and you can plug in the rest of the stuff and get an answer. So you can predict where these vibrations are going to happen, but this is not a physics class, so we're not going to focus on that. I just want to show you the equation. And then, of course, we can use this equation to come to conclusions, right? Basically, the strength of the bond, you see we have this F force constant. If that number gets bigger, if the bond is stronger, then the wave number is higher. And so a triple bond is going to have a higher wave number than a double bond, and that's going to have a higher wave number than a single bond in general. And triple bonds are shorter, right? Remember from lab 1, a single bond is capable of rotating. Well, once you have a double bond, you can't really rotate it anymore without breaking it. It's a lot more stiff, it's shorter. If you have a triple bond, you have a really short, stiff, strong bond. That wave number is going to be higher. You're going to see that closer to the larger numbers. So the strength of the bond, the masses of the atoms, right? Which one is going to vibrate more strongly? An oxygen-oxygen or an oxygen-hydrogen? Well, hydrogen's molar mass is 1, oxygen is 16, right? I don't have 16 fingers, but 16. So it's going to be like a paddle ball, right? The hydrogen's going to be just paddling against that oxygen. So it depends on the size of the atoms. It depends on the polarity of the bond. It depends on the type of bond. Is it a single, double, triple bond? Those things are going to affect your wave numbers. Does that make sense? Any questions about anything so far? This is just the theory behind it. You're not expected to know wave number formula. No, no, no. Okay, sounds good. So on to the next slide. So this is kind of like what I was showing you last week where I did the water dance, again, open up a yoga studio, talk about the motions of the molecules, move just like molecules do, right? You have your, somebody told me that it's also like a cheerleader thing, right? Like you can like the pom-poms are like, go team, right? You could do it like symmetrically. The bonds can stretch. You could do it asymmetrically. So like one pom-pom is out while the other one is in. You could do like a forward, like, okay, let's go. Who's the best, right? Like things like that. You could do it like anti-symmetrically as well. Depends on the shape. This is just a very simple model of just 3 atoms and 2 bonds. The more bonds, the more vibrations. So the more signals, the more peaks you're gonna see, right? I'm gonna show you some actual animations so you see what I'm talking about. But this is just a very visual, like, you know, primer to it. Again, I want to emphasize that you need a change in the dipole. If your dipole is not changing because of symmetry, because of canceling out, for whatever reason, you are not going to show up in IR. So look at this molecule here, carbon dioxide. It has a polar bond, right? Carbon oxygen is a polar bond, very strong bond. But because carbon dioxide is a linear molecule, the dipoles are actually in opposite directions, right? This could be, let's call it 1. Well, this would be -1. 1 plus -1 equals 0. They cancel out. So that stretch does not appear in IR. There is no dipole change. In fact, the dipole just completely cancels out. Make sense? I have a question. It says, would double bonds of carbon be present in wave numbers? It depends, right? Because sometimes if the whole molecule is symmetric, then that stretch will be symmetric as well. But if you have an asymmetric molecule, even though that's a symmetric stretch, the whole asymmetry is going to create a change in the dipole. I'll show you with the animations. I know what you're thinking. I understand where your mind is. So hopefully once you see the actual motions of the molecule, your question will be more cleared up. But yeah, you're thinking correctly. You're thinking very correctly with that question. Thank you. So in carbon dioxide, you can also have a stretch where this one might be a little bit bigger than this one, right? Imagine having like Arnold Schwarzenegger playing tug of war with like a 5-year-old, right? Well, of course, Arnold is gonna like take that guy and flip him to the back because the little kid weighs barely anything and the other guy's gonna win. So similarly, if there's like one vibration in one direction, well, that one has a higher magnitude, so they don't completely cancel out. So that asymmetric stretch in carbon dioxide, you will see that in IR. So you can have a molecule that doesn't show up at all. You can have a molecule where only some of the stretches are going to show up, or you can have a molecule where all of the stretches are going to show up. It depends. It really depends on the structure, on the symmetry. You got to consider all these factors. Okay, so I'm going to show you the animations so you can see better what I'm talking about. So let me make sure there's no more slides. Yep. So this will be the next section. Right now, I'm going to show you the website that I like to use. Okay, so here we go. And then let me move this to the bottom. Here. This is called CHEM223A. Everybody can see my screen, right? You can see a water molecule on the screen. CHEM223A. I've used this website for a while now, 10 plus years. I just used it last week to talk about one of my projects in my quantum chemistry class. Very useful website. There's a lot of 3D models that have been derived from X-ray crystallography, so we know exactly what they look like. We know their bond lengths. We know their planes of symmetry, all sorts of information. You can get this and drag it around with your mouse and play with it. And you can see there's like organic examples. You can look at like, electrophiles, oxidations, things like that. Inorganic, if you ever take the class. Right here, you can go to structure and bonding, and where it says molecular vibrations, you would click where it says water, and you get to this page right here. I'll post the link in the announcements at the end so you guys can see it. So you see that we're expecting some stretches and some bends. We have one bend and two stretches. And the stretches are the symmetric, like pom-pom stretch, and the asymmetric pom-pom stretch. So here, you can click to show the vibrations, and you see we have only 3 of them. So let's look at the one with the lower wave number. Remember, low wave number, low energy. So this is the lowest energy vibration. Let's see what it looks like. All right, there it is. Go team, go. Go team, go. You can do it. Looks like Kirby in Smash Bros. When they're like, it's like doing that, right? So this is a bending motion. Notice that the molecule is bending. The bonds are not actually compressing and contracting like a spring. The whole molecule is just bending. So bending in general, bending vibrations have lower energy than stretching vibrations. One more time. Bending vibrations generally have lower energy than stretching vibrations. And you can see that this is only at 1711 wave numbers, right? 1711 wave numbers, 1711 inverse centimeters, same thing. Let's look at the next one. Look at the jump. It goes from 1711 to 3730. That's almost double. That's almost twice as much. And look at that. It's actually a stretching motion. They're both symmetrically stretching at the same time towards the oxygen. And again, even though this stretch itself is symmetric, the vectors of the dipole do not cancel out. It is not -1 + 1, 0. No, they're both pointing in the same direction upwards. So they actually add together and form a third vector. And that's why this stretch is still visible in IR, even though it's in a symmetrical molecule and the stretch itself is a symmetric stretch. The dipole vectors have to cancel out completely if it's going to disappear from IR. I'll show you more examples so you know what I mean. All right, so this one happens at 3730. Let's look at the highest energy one. There it is, the asymmetric stretch. And again, you'll notice both of the dipoles are pointing in one direction, so they do add up and form a larger dipole. And that's why this one is also apparent in IR. It is asymmetric. It is polar. Oxygen and hydrogen form a polar bond. So this is a very strong energy vibration. That's why you find it at 3851, 3,851 wave numbers. What happens if I add another bond? What if I had like another H bond to this atom? Well, let's find out. I'm going to go back to where it says molecular vibrations, and I'm going to click on ammonia, NH3. So here's ammonia, right? It looks just like water, but you have that extra hydrogen bond right there, and of course you have a nitrogen. We expect more vibrations because there's more atoms. That's just true. You can see here, right here, 3n minus 5 frequencies for linear systems and 3n minus 6 for nonlinear systems. Well, this is a linear system, and we have 4 atoms. 3 times 4 is 12 minus 5 equals 7. So we should have 7 vibrations. Let's check. 1, 2, 3, 4, 5, 6. Okay, I must have done my math a little bit off, but yeah. So we have 6 vibrations, or maybe one of them is just not IR active at all. Regardless, you see we have more vibrations than a water molecule. Make sense? More vibrations than a water molecule because we have more atoms. The more atoms you have, the more vibrations you have, the more peaks you are going to observe in your infrared spectrum. So let's take a look at the lowest energy one. It's a bend. Right away, I know it's a bend because it has the lower energy. So there it is. This is the symmetric out of plane bending. And it's symmetric because all 3 atoms are bending out of the plane towards each other at the same time with the same intensity. They're going in the same direction, so there is a net dipole change. So we do observe this at 1,132 wave numbers. Let's take a look at the next one. 1727. This one is asymmetric, right? Looks like a penguin swimming in the water. Know that. Stretch that back. Yeah, very nice. Alrighty. Let's look at the next one. 1727. It's kind of like an asymmetric stretch. Yeah, this is very asymmetric. So definitely a dipole change here. Remember that ammonia is trigonal pyramidal, so it is not a flat molecule. So even if you look at it like this, you'll be like, well, that looks flat. No, it's trigonal pyramidal. It's sp3 tetrahedral electronically, but trigonal pyramidal. So this is where all that knowledge starts to kick in. And so you need to have a good background, good fundamentals to talk about this. Okay. And then you'll see so far we have all of our vibrations in the lower 1000s, upper 1000s, and suddenly we make the jump to 3000. Hold on, I just saw there's a question. Okay. Looks good, looks good. So it suddenly jumps up to the 3000s. So now the 3000s are the stretching vibrations. Let's take a look. Look at that. Oh, that looks nice. I wish somebody would do that to my back. Just like, Mr. Incredible style, like stretching right there. This is a symmetric stretching. This is a symmetric NH stretch. That's what we call it. And you can see that it happens between a polar bond. Nitrogen and hydrogen is a polar bond. Hydrogen is a lot lighter than nitrogen. So the arrow is very large and it happens symmetrically. So even though it's happening symmetrically, again, the molecule is not flat. So there's still a dipole changing towards the bottom. This is going to appear. This is going to show up. Let's look at the highest one. Let's just go to the highest energy one. There you go. That's another cheerleader like kind of movement right there. You see? So yeah, like go team, go team. But this is an asymmetric stretch. So I'm guessing the one below that is the symmetric one. Yeah, it's kind of symmetric towards the bottom. And again, you see the little arrows right here on these two, and you see the larger arrows on this one over here. So it just depends, there is a class that teaches you how to predict all of these things. That is Advanced in Organic Chemistry number 2. It gets pretty crazy. They use the same mathematics as the Rubik's Cube to solve these problems. So yeah, pretty wild. Fortunately, we just have these animations and they can show us right away what would take mathematicians a while to calculate. So let's look at another molecule. Let's look at benzene. Benzene is a very symmetrical molecule made out of only carbons and hydrogens. Look at that. So again, now we have 12 atoms, 6 carbons, 6 hydrogens. It is a nonlinear system. Let's see. So 12 times 3 is 36 minus 6. We should have 30 vibrations. Let's check it out. I'm not going to count them all, but I mean, that looks like a lot, probably 30. So you see how as we make the molecule more complex, we start having more vibrations just because we have more possibilities, right? So let's look at the lowest energy one. Once again, it's a bend. It's an out-of-plane bending. And you'll notice that it is bending out of the plane, but very slightly, right? Some atoms more than others. The double bond is a stronger bond. It's a stiffer bond, so it takes more energy to really change it. In this case, you would find this at 466. We might not even see it. It's a bending vibration. It's very low energy. Let's go and contrast that with the highest energy vibration. Look at that. That looks real nice, right? A symmetrical carbon-hydrogen aromatic stretch. That has the highest energy. You can find that one at 3385. But in this case, you'll notice that these two are canceling out in opposite directions. These cancel out in this direction, and these cancel out in this direction. So all of your vectors, all of your dipole vectors are canceling out. So even though this is an actual motion that the molecule experiences, we will not observe this signal in IR because all of the dipoles are canceling each other out symmetrically. So this is another example where that happens. It does have asymmetric signals that are going to show up. So let me show you one of those. I think it's the next lowest one. So this is a signal that is not entirely symmetric, right? It has all of the vectors pointing in the up direction in general. Even if it's a little tilted, they're all still going in the upper direction. So this one is going to show up in IR, and it shows up at 3370. What do we call this one? I don't know. You could start coming up with names like the symmetric, spring. Some of them are going in and some of them are going out. This one, some of them are going out while some of them are going in while some of them are going out. I mean, you can play around with possibilities and combinatorics and all that other stuff to come up with this. This is a very symmetrical one as well, but notice that the arrows outwards are bigger than the arrows inwards, so this will show up in IR. And again, you can just go and see all sorts of, this is like a weird bending motion that happens there. Yeah, CHEM223A, really great website. I'm gonna post it in the announcements. Make sure you play around with it because it's very beautiful website, very nice. It comes from real data, so this is actually what is happening. Let's look at one more. We're gonna look at vanillin because we're actually gonna work with vanillin, I believe, for lab 6. Lab 6, maybe lab 5, I'm not sure. But we're gonna be working with vanillin pretty soon. This is the flavor that gives vanilla its flavor, its smell. So when you smell vanilla, this is what's going into your nose right here. So we have 3 functional groups. We have this oxygen, hydrogen right there. That white one is hydrogen, that red one is oxygen. So this is OH on the top left. You have carbon, oxygen, carbon bridge. That's an ether. And at the very bottom right, you have the carbon double bond oxygen. That's a carbonyl, but that hydrogen makes it an aldehyde. So this is an aldehyde. I'll explain more about carbonyls pretty soon, but we have 3 main functional groups here. But my professor said that the ring is a functional group. If that's what your professor says, then that is true, right? Some chemists will tell you that the ring is the main structure and everything peripheral is the functional groups, right? I agree with that perspective, but some of the more seasoned, more experienced published chemists consider it to be its own functional group. So whatever your professor tells you is true. Regardless, it all vibrates, man. They're all vibrations. It doesn't really matter. What we're looking for are specific vibrations because remember, it takes a specific amount of energy to vibrate a specific bond. Just like it takes a specific amount of money to purchase a Lamborghini or something, you need that specific amount of energy to vibrate that bond. So here, I'm not going to count how many atoms we have. I already know we have a lot, so we're going to have a lot. Let's take a look. Look at that. That's a lot of vibrations. As low as 71, as high as 3783. Let's start with the highest energy one. See what we observe. So there it is. Very interesting one, right? Only the oxygen-hydrogen bond is vibrating. Nothing else. This is, again, the car only costs 5,000. It doesn't cost 4,000. It doesn't cost 4,500. It doesn't cost 6,000. It costs exactly 5,000. So this molecule, this bond, vibrates by itself because it has its own price of energy, its own amount that it needs to vibrate. And that happens at 3783, 3,783 wave numbers. And it's only that oxygen-hydrogen bond that is vibrating. So in that region, you will see only the signal for only the OH. And that is how we can find out what the functional groups are, because they each have their own unique vibrations that only happen in specific places. So in this case, you might see an IR spectrum. You'll see a peak at 3783, and you're like, oh, I know that's where alcohols like to hang out and vibrate. So that's probably an alcohol peak right there. And 90% of the time, you might be correct. Because it is unique. And so notice the rest of the molecule does not vibrate. That's because they require a different energy price, a different energy amount to vibrate. So let's take a look at the next lowest one. Look at that. Again, notice how the rest of the molecule is not vibrating. This is a very specific characteristic vibration. This is a carbon-hydrogen stretch of an aromatic ring. Carbon-hydrogen stretch of an aromatic ring. That happens at 3262. You can see this peak for sure. Very sharp peak. I'll show you later. Let's look at the next lowest one. That is another one. That is the other type of carbon-hydrogen aromatic stretch. Only this singular one. This is also a very sharp peak. You can find that at 3233. And then let's look at the last one here. Look at that. This is what's called a methyl sp3 CH stretch. And it's only this one. Notice there's no other methyl groups in this molecule. So only the methyl is vibrating at only this specific wave number. I hope that you're starting to see what I mean. Each functional group has its own energy that it vibrates at. Let's see if we can find the one for this carbonyl. I know carbonyls like to vibrate at around 1700, so let me see. There's no 1700. It must be this one, 1699. Nope, that's a whole bunch of bends. Look at that. You see how the yellow arrows are tiny? So that's not a lot of motion happening right there. Very weak signals. So it must be the next one. Yes, there it is. Look at that. This aldehyde, the carbon-oxygen double bond right there, is vibrating by itself. There is a slight bending motion on the lower double bond, but this is strictly like its own vibration right there. And that happens at 1848. And notice that nothing else, apart from the slight wiggling, nothing else in the molecule is actually vibrating with that same intensity. So again, hopefully this illustrates in actual visual terms how the vibrations only happen at specific energies. And so when we look at the chart, we look at the values of those specific energies and we see if there is a peak. And then what kind of a peak? Is it a strong peak, a weak peak, a broad peak, a narrow peak, blah, 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 blah. But this is it. So I encourage you over the next 2 weeks, please come over here and play around with ChemTube 3D. They have all sorts of really cool like compounds. Look at this one. And you can just play around and be like, look, you have all sorts of different vibrations and you can see how they all move and how they wiggle. Yeah, look at this one. That's a nice dance move right there. Yeah. So just come over here, ChemTube 3D. There's also other websites. So I found this one from Purdue. This is more accurate in terms of how fast they're actually moving. Remember, molecules are literally atomic size. So they're moving pretty quickly. These vibrations are happening so incredibly fast, right? But not so fast that we can't detect them. They're infrared fast. And you can click on your molecules like CO2, and it'll tell you if they are IR active or not. So it tells you here, Raman inactive, IR inactive, and it shows you, and you can also take the molecule and drag it around as well. So this is from Purdue, Chem Purdue, molecular vibrations as well. Let's look at methane. This is all the ways that methane likes to move and dance. So any questions about this? I'm going to go back to the presentation now, but any questions about the dances of the molecules? Okay. All right. So now that we've seen that, now we can actually talk about the graph. Now we're not just going in blindly into this. All you guys see is a bunch of squiggly lines and curves and peaks. But now we know what these numbers mean. So once again, if you look at the x-axis, you'll see wave number. So we look at three things. We look at wave number, we look at the shape, and we look at the intensity. So the wave number is your x-axis. Let me annotate here with my little pen. Here we go. This is your x-axis. So that's this wave number. Again, 400, low energy. It's a low number, right? It's a small number. 4,000, high energy. So when you tell me about these peaks, you need to give me numbers. You can't just be that one in the center. Which one? Give me the number. You actually have a scale. Don't be exact. Don't be like, 1,737.5. You cannot possibly know that, right? Significant figures. Make your best guess, and it will generally be considered acceptable. Okay? So, for example, what would you say the value of this one right here is? You guys actually have to answer me here. What would you say the wave number for this peak is? Be an answer in the chat. 3350. Let's see, 31. Yep, that looks about 3350. Yep, that would be considered acceptable. Yes. It could be 3355, 3357, right? That's the whole point of significant figures. We can only guess up to what we're given. We can't make that much exact measurements. So yes, that would be a peak at 3350. So if you have a question about it, you will ask me, hey, that peak at 3350 wave numbers, what is that? Now I know which one you're talking about. Okay? So we look at wave number, that's in your x-axis, it's energy, low number, low energy, high number, high energy. Then we look at the shape. And by shape, we mean the shape. Like, what does it actually look like? We have very specific words to talk about shape. I'm going to use the color green just to change it up. So, for example, let's look at the peak at 3350 right here. The same peak we were just talking about at 3350. How would you describe it? What kind of shape does it have? Is it narrow? Is it sharp? Is it blunt? Is it broad? Is it smooth? Is it rough? Is it jagged? Like, what words would you use to describe this peak right here at 3350? Broad, right? That's definitely a broad peak. It's from around 3,200 to about 3,600, right? So 3,200 to 3,600. That's a difference of 400 wave numbers. That's pretty broad to me. All right. So you can call this a broad peak for sure. What else? What's another word we can use to describe this? Smooth. Excellent. This is a smooth peak. Compare that to this peak over here at 1500. I'm going to use the color pink. How would you describe this peak right here? Just the shape at 1500. How would you describe that peak? Sharp, right? Sharp, pointy, for sure. Narrow, exactly. It's much narrower than the broad peak at 3350, right? These are the way we talk about these peaks. These are the words we use. This is the language that we speak in, right? So when you guys are given charts, when you're given questions, you'll read stuff like this. You know, the sharp medium peak at 1500, which one is that one? And you should know that I'm talking about the one in the pink, right? The last thing we look at is also the intensity, which is just your y-axis. So you look at your y-axis, that tells you the intensity. The closer it is to zero, you see how it goes from 100 to zero? The closer it is to zero, the higher the intensity of the peak. The peak itself is intense. The absorbance is intense. The transmittance is weak. That's why it has a low number. But basically, the lower it hangs, the more intense the peak. Okay? You can think about it like that. So this would be a strong or very strong peak. We usually say VS, very strong, or we just write it out, very strong. These are also very strong peaks. Very strong, very strong. It's below 20% transmission, right? Almost 10% for some of them. So this one's like at 3%. This is definitely a very strong, sharp peak. You see that? And also, you'll notice that all of these peaks kind of blend together up here. So like the signal is broad, but the peaks themselves are sharp. Okay, this is just semantics, linguistics. And so it's strong. What about this one? This one here is at like 30%, right? This one over here. That one's at about 30%. So it's strong, but not as strong. It's closer to 50. I might call this one medium strong. Medium strong. Some people will tell you, well, it's strong and this is very strong. Tomato, tomato, potato, potato. Coriander is cilantro and parsley and cilantro and chickpeas are garbanzos. It's all the same thing as long as you kind of get the gist of it, right? Like if you call the peak at 1500, if you were to call that weak, that's just wrong. Like you cannot possibly look at this and see that it is below 50 and call it weak. No, 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 no. This is a strong peak. Look how low to the ground it is, right? So you got to look at that. So we use words like strong, we use words like weak, very weak, medium, medium weak, medium strong, very strong. We don't say very medium, that doesn't make much sense. So we usually kind of divide it in quarters. Like if it's from like 100 to 75, it's weak, very weak. Between 25 and 50, it's like just weak, like, medium weak. Then we get to medium between 60 and 40. And then anything like below 30 is generally considered strong, very strong. So now we know and we have the language to describe it. We can say the medium strong peak at 1500 wave numbers, the medium strong sharp peak at 1500 wave numbers, or the very strong broad peak at 3350 wave numbers. You see, this is how we start speaking organic chemistry. This is how we speak spectroscopies. So any questions about the words, the things that we look for? So in your quizzes, you will be given these words and you have to know what they mean, like what I'm referring to. So make sure you practice. The more practice spectra that you do, the better. And I'll give you guys resources for that at the end. Okay. So this is the secret right here. Finally, what you've all been waiting for. This is how we know what's what. We have the whole spectra, 400 to 4,000. Here they cut it off at 600 because it's probably from an older textbook. In general, it's usually from 400 to 4,000 or a little bit more, a little bit less. Remember, single bonds are weaker than double bonds. Double bonds are weaker than triple bonds. So the single bonds are going to have lower wave numbers than double bonds, and the double bonds are going to have lower wave numbers than triple bonds. And then the polar bonds are even stronger. So those, even though they are single bonds, they're polar. The polarity gives them more strength. And so those are going to have generally the highest wave numbers of them all. So just take a minute to look at this. On the top, you see wavelength. Well, wavelength is just another way to express wave number. And then you see the percent transmittance with 0 at the bottom, 100 at the top. So we're going to see examples, right? But in general, you should kind of get this in your head. Get into your head like, single polar bonds are over here. Double bonds are here. Triple bonds are here. And single very polar bonds are the highest wave numbers of them all. Are there any questions about what you're seeing here? Let me know. Actually, like take a minute and like really look at this. So this is how we know. We've done math. We've done actual experimental observations. We've compared it. And this is the information that we've been able to compile over the last 50 years. Pretty neat. I don't know how chemists in the 1800s used to do chemistry without all these analysis and everything. Like they still figured out molar masses and formulas, but they had no instruments like this. So I mean, that's how you know like you have to really be like in another dimension to be thinking about these things. Alrighty. So let's look at some actual workings then. This is it. Now we're getting into the details. We have the theory behind us. We've explained that molecules vibrate in all sorts of different ways. We've been telling you that there are functional groups that are vibrating. Now let's actually look at what those vibrations and peaks look like. So let's start with the most basic type of molecule, a carbon, hydrogen only hydrocarbon molecule. You can have single bonds, alkanes, alkenes, double bonds, or alkynes, triple bonds, right? All kinds of hydrocarbons. So the triple bond is stronger than the double bond. The double bond is stronger than the single bond. So if you look down here at the bottom right, this is an sp triple bonded carbon hydrogen stretch. You see that there is a peak at 33 or 3,300 wave numbers, right? 3,300, that's what I meant to say. And it is a weak, sharp peak. That, if you see that, that is going to be a carbon triple bonded hydrogen stretch. If you see an alkene, a double bond, you're going to also see a weak, sharp peak. And its wave number is going to be a little bit less than the triple bond. So you see it goes from 33 to 31. 3,300 to 3,100, 3,300 to 3,100. It lowers because the double bond is weaker than the triple bond. That makes sense. And finally, the single carbon hydrogen bond, well, that's the weakest of them all, right? So you're going to see that one at 2,900 roughly. And that peak that you have been observing, notice how it gets more towards the right. It flat out disappears because it comes in between this giant broad signal. This signal right here, I want you guys to look at this entire shape, this entire thing right here. I'm gonna call this the stalagmite. If you guys have ever seen pictures of a cave, you see that there's like these very pointy, spiky formations at the top. Those are called stalagmites. If they're on the ground, they're called stalagmites. So these are stalagmites. That's what I call them. Other people have different names for them. These are everywhere. This pattern right here, this stalagmite looking very strong signal is going to be present in almost every single spectrum, like 99.9% of your spectra. Because if you're studying organic chemistry is the chemistry of carbon. And carbon wants four bonds, and if it doesn't find any other atoms, it will bond to hydrogens. So every organic molecule has carbon-hydrogen bonds in it. Almost every, 99% of them do. So 99% of your spectra are going to have this signal, no matter what. You need to know what it looks like. You need to know what it is, but it's everywhere. So sometimes it's not very useful. But this is present in every spectra. Look at the alkyne. It's right there, right? It's right here. Look at this. Look at the alkene. It's also right here. Look at the regular alkane. It's right here. It's just that when you have a double or a triple bond, you get this extra weak, sharp peak. Another way to think about it is through hybridization. The closer you are to an S, right? If you're more S character, like SP, you have a higher wave number. So the closer you get to p orbital, the less wave number you have. So this is high wave number over here with S, high wave number, and this over here would be lower wave number. Many different ways you can think about it. I like to think about it just in terms of strength, right? I just know that triple bonds are stronger, so they have a higher wave number. And also notice that there's not much else, right? There's not that many peaks on this graph. So there's not other functional groups. There's no alcohols. There's no carbon double bond oxygens. You might be like, what are these peaks right here? These are also very typical of alkanes, alkenes, alkynes. This is just CH bending right here. Remember that bending vibrations have lower energy than stretching vibrations. So the fact that you're seeing some peaks at a lot lower wave number, those are likely bending. You don't have anything else. It's a hydrocarbon, so it obviously must be a carbon-hydrogen bending vibration. And that's it. You don't really have much else. So again, you're still learning right now. We're just learning it in the past hour, 2 hours, so I don't expect you to have it 100% in your brain yet. This is very pattern recognition. So the more you do, the more patterns you recognize, the better you get at doing IR. So let's look at the next example, and we can see how to analyze it. Octane, gasoline, high octane, right? Just a boring old carbon-hydrogen chain. It's no double bonds, no triple bonds. It's just carbon-hydrogen single bonds, sp3. So what do we observe? Well, when we look at these spectra, let's always start with the higher wave number, right? So let's start over here at around 4,000, 3,000. Let's see if we see anything. What do we see? Well, I see the stalagmites, right? Look at this. Stalagmites. Well, I know these are my sp3 CH stretches. How do I know it's sp3? Because I was told this is octane. And here's the structure of octane right there. It's just carbon with 4 bonds everywhere. All of it is sp3. There is only carbon hydrogen. The stalagmites are sp3CH stretches. So far, so good? And you see there's no other signals, right? There's nothing here. And finally, we get a signal at around 1450. These are your CH bending. This is your CH bending. You don't have to be specific about which is which. I don't expect that level of detail, but you should know that those are bendings. You cannot call this CH stretch. That's wrong. Why is it wrong? Because stretches take more energy than bends in general. That's how I know you're guessing. And so again, the stalagmites are everywhere. They are in all 99.9% of spectra. So you have to be able to point them out. Let's look at the next example. Any questions before I move on? There's only one type of bond here, so you don't see a lot of peaks. You don't see a lot of signals. Very clean spectra. Okay, so let's look at the next example. Another type of hydrocarbon, but this one is aromatic. That means there's a benzene ring somewhere in there. So the benzene ring, when you add an aromatic ring to a compound, it makes all of the peaks sharper. So look at the previous one. The octane, it looks kind of sharp. Not really the best example. So yeah, maybe this one. Look at the stalagmites, right? They're kind of sharp, but they're not like kind of sharp. Like you still have a very broad signal. But look at this one. Almost all of the peaks are extremely sharp. They look like needles. And also look at the intensity of your stalagmites, right? So again, the stalagmites, your CH stretches, they are always at around 3,000, 2,900. But in this case, they're not very intense. They're very weak. They're weak or medium at best, right? So these are your stalagmites here. But because of the aromatic ring, because of all of that stuff happening in there, remember, double bonds are stronger, so it takes more energy, so the intensity goes down. The intensity goes down. So you see very characteristic peaks. You see this really sharp peak right here at exactly 3,000. This is that carbon hydrogen right there. You also saw it in the animation with benzene. There was that singular carbon hydrogen vibration. That's that peak right there. Very sharp. The other ones are still CH3 stretches. All of these are stretches. When you have an aromatic ring, you get this interesting pattern up here. We call these combination bands. They almost look like little hills. Very, very weak signals. Sometimes they get absorbed by other signals, so it's very hard to see. This is a very simple hydrocarbon aromatic compound, so we can see them. This will give you a hint that what you're looking at is aromatic and there's probably a ring in there. If you have a ring, like a benzene ring, you obviously have double bonds, so you're going to see a double bond peak at around 1450, 1500. So this right here, you can say is your aromatic carbon-carbon double bond stretch. Probably this one as well. It's one of those weird ones that we saw. We don't know exactly which one, but I mean, hey, as long as we see one of the two. What about these right here? Well, the wave numbers are too small, so that's already starting to go to the fingerprint region, and they are very weak. They're probably some sort of CH bends. But I mean, at this point, we're just kind of like looking for whatever else we can find, right? Once you get to the more advanced level, you can tell me if this is like para, ortho, meta, but this is diet OChem, so we don't worry about that kind of stuff. In short, we look for characteristic peaks. We start with the highest wave numbers, and then we move our way down. So any questions about this? And notice it looks a little more complicated because we just have more bonds. We have the benzene ring, but it's still relatively simple. It's not very noisy. It's not very messy. Okay. So moving on to the next slide. The carbonyl. Finally, the carbonyl. Okay. So this is where I have to take a moment and really emphasize that in this class so far, I have asked you to be very specific. Be very specific with your words. They mean different things. In this case, I need you guys to understand this right now. When I say the word carbonyl, I am only talking about carbon double bond oxygen. That's it. This is not its own molecule. This is a component of a molecule. Just like, my thumb is a component of my whole being, right? If I just show you my thumb, you're not gonna be like, oh, that's Eduardo Vite. No, this is just one part of the whole. A carbonyl is a component of the whole functional group. It has its own name, just like we call this thumb and we call this pinky. If we see a carbon double bonded oxygen, we call that a carbonyl. There are functional groups that contain carbonyls. Think of it like a first name and a last name. right? Back in the day, the Spanish conquistadors, they were like, have all these crazy last names. You know, if you're Hispanic, you know, you have like a million last names or anything. So what's your name? I am Juan Ponce de Leon, right? Or maybe like if you watch Lord of the Rings or you've seen any sort of medieval thing, it's like, who are you? I am Aragorn, son of Arathorn, right? Um, First name, last name. Well, my name is carbonyl of the amide group. My name is carbonyl of a carboxylic acid. My name is ketone. I'm sorry, my name is carbonyl of a ketone. My name is carbonyl of an aldehyde. My name is carbonyl of an ester. All of these groups are independent functional groups, but they all contain carbonyl. So it's like a last name, right? But backwards, depends. I think I think the Vietnamese people do the family name first and then the given name later. So yeah. So again, here are your functional groups. They are all their own functional groups, but they all contain a carbonyl. They all contain a carbon double bonded oxygen. So when you are pointing out a signal to me, if you're gonna point out a signal and you're gonna tell me this is a carbon double bond oxygen, you have to call it what it is, a carbonyl. This is a carbonyl signal. If you point to it and you say carboxylic acid, it's wrong because the carboxylic acid has a carbonyl and it has a hydroxyl. Which of the two are you talking about? You have to be specific. One is called hydroxyl, one is called carbonyl. So when you're talking about peaks, you have to use the specific words, the specific names. This is why you need to know your functional groups. A very common mistake is that people call a carbonyl a carboxylic or a carboxylate. No, that is not true. That is not true. So the carbonyl, the carbon double bond oxygen, likes to vibrate at 1700, roughly. I like this rule. 1700 plus minus 50. Right? 1700 plus minus 50. Sometimes a little bit above, sometimes a little bit below. Remember, everything in life is a Gaussian distribution, right? So obviously there's always some rare exceptions. But for the most part, 1700s plus minus 50, you're going to observe your carbonyl peak. And remember that some bonds are stronger and more polar. So the stronger, more polar bonds are going to have higher wave numbers. So like if you look at the carboxylic acid, I'm going to use the color blue. I can't seem to erase that circle I drew, not sure why. But you have a dipole in this direction and you have a dipole in this direction. That creates a lot of polarity. There's a double and single bond right there. That takes a lot of energy to vibrate, so it should have a higher wave number, 1710 to 1780. Look at the ester. Very similar structure, right? Two dipoles, but here now you have another dipole to a carbon. So this one's going to have strong, but not as strong, right? It only goes up to 1750 compared to 1780 with the carboxylic acid. Look at the amide. You have your carbonyl and you have your carbon nitrogen single bond, and you have another one in this direction. So it's also polar, but not as much compared to the carboxylic acid, not as much compared to the ester. The wave number is smaller. Look at the aldehyde. You have the carbonyl this way, and now you have another dipole with a heavy atom, the carbon, and a light atom, the hydrogen. So that carbon hydrogen is like a paddle ball. That's its own vibration right there. That's why aldehyde carbonyls are very unique as well. And then you have the plain old regular ketone. So this is a common mistake. People call a carbonyl, they'll just say ketone. Eh, no. A ketone contains a carbonyl, but so do other things. A carbonyl by itself is not a ketone. Do not call it a ketone. It's a carbonyl. That is wrong. That will cost you points. So be very specific, right? First name, last name, right? I am carbonyl from amide. I am carbonyl of carboxylic acid. I am carbonyl of ketone. First name, last name, vice versa, right? So it just depends. And again, I want to emphasize these numbers are not absolute. They are not exact. It is not always a ketone at 1715. It is not always an ester at 1735. Depending on the rest of the molecule, depending on the polarity of the whole molecule, some of these numbers are gonna, vary a little bit. That's why my own general rule is 1700 plus minus 50. If you follow that rule, you'll be pretty good about 95% of the time. Any questions about carbonyls? If you learn nothing more from IR, you have to learn that the carbonyls are at 1700 plus minus 50, right? The mitochondria is the powerhouse of the cell. You remember that? So please remember that carbonyls vibrate at 1700 plus minus 50 wave numbers. Okay? It's like not knowing who Bugs Bunny is. It's like not knowing who SpongeBob is. It's like not knowing Gandhi. It's like not knowing like it's so iconic. It's like you took OChem and you don't know what a carbonyl means. Like okay, you must have had a bad professor. So, make me look better. Remember what a carbonyl is, please. Alrighty. Okay, so let's look at some actual examples. Here are two compounds that contain carbonyls. They are different functional groups. One is a ketone, one is an aldehyde, but they both contain a carbon double bond oxygen. Where do we find it? At 1700 plus minus 50. So look, this very strong, I guess we can call it sharp, very strong, sharp, intense signal is your carbonyl stretch right here. This is your carbon oxygen stretch. Look at the one below, butyraldehyde. That one's a different functional group, but it has a carbonyl. It's at 1720, right there. This is your carbon double bonded oxygen right there. Look how strong that is. That is a very strong signal. That's like 3% transmittance. That's like almost complete absorption right there. Carbonyl is a very, very absorptive bond. It absorbs almost all of its energy to vibrate. And that vibration is very polar, so it causes a very strong signal. What's over here? What's this at 3000? What are these things? Somebody tell me, please. What are those stalagmites? What are that? What is that? What kind of stretch is that? They show up everywhere, remember? What is that stretch that you're seeing there around 3000s? CH, that's right. These are your CH stretches. They are always present because it is an organic molecule. Every organic molecule has carbon-hydrogen bonds by definition. So these are always present. Look at the bottom, they're present. They look a little different, right? But they're present. So how do you tell the difference between a ketone carbonyl and an aldehyde carbonyl? Well, the key is here. I'm going to use green. This carbon-hydrogen bond that is directly attached to the carbon-oxygen carbonyl of your aldehyde, that has its own unique vibration. And it has a slightly lower wave number than the typical CHs that you find at 3000. So you see there's a peak at 2720 and 2820. Those peaks are that carbon-hydrogen, that carbonyl carbon-hydrogen stretch right there. And I showed you earlier in the animations exactly what an aldehyde looks like. So if you look at the top, it looks just like your standard run-of-the-mill stalactites, no big deal. But if you look at the bottom, they look a little different, and some of the peaks are a little lower than the rest. And also, just look at your structure, right? They give you the structure right there. You can see that there's an aldehyde, so you should expect an aldehyde CH stretch. You don't go into these blindly. You don't just get it without a formula or a name or an expectation, right? That's not possible. You have an idea of what you're working with when you're doing these analysis. You just have to justify, you have to explain, you have to make educated guesses. So you're gonna ask me, I'm gonna use the color green. Well, what's all this? I don't know. Probably some CH bends, probably some WAGs. What is this? I don't know. That's in the fingerprint region. We don't really look at it. What about these? I don't know that there's much else to really look at. So this is again probably some CH bends. You can just say they're bending vibrations, bending. As far as we're concerned, since we only have a carbonyl in these structures, we don't really look for anything else. So that's my point. We don't always use all of the signals. We use the ones that are characteristic. Any questions about this? Let me check on the time. Okay, we're doing good. All right, let's look at more examples. So we've talked about carbonyls, we've talked about alkenes. Well, when you put them together, you get something interesting. So in organic chemistry and in biochemistry, you're going to see this word, conjugation, a conjugated system. What does that mean? It is simply a double bond, single bond, double bond, single bond, double bond, single bond system. Alternating single double bonds, right? Remember that one meme from middle school where you have like that little S right there? It's kind of like that. You can make infinite chains of it, right? It's kind of like that, but its own unique thing. It's a double bond, single bond that is alternating. And so that double bond, it could also be a carbonyl, right? So you could have, for example, carbonyl, single bond, double bond, single bond, double bond, single bond, carbonyl, single bond, double bond, etc. As long as you have an alternating system of single and double bonds, it is called a conjugated system. Now, I had a quick question. It says, does the fingerprint region always start at 1500? No, no. I think the fingerprint region starts at 1000 and below. Other people will tell you 1200 and below. Some people will tell you 1400. Um, as a rule of thumb, I would say anything below 1200 is fingerprintish. But really, 1000 and below is pretty much for sure fingerprint. So, yeah, good question. Good question. Yeah. Alrighty. So, again, conjugated systems is just alternating single double bonds. When you have that alternating single double bond, you create resonance in the structure. When you have resonance, you are spreading out that negative charge. You're delocalizing it, right? A delocalized system. So your double bond gets weaker. It turns into like 1.5 bonds, right? That's why we draw it with the little dash line over here on the right. The double bond is less than a double bond. The single bond is more than a single bond. It's in between. So that means your wave number goes down when you have a conjugated system in your molecule. So just to give you an example, down here, this ketone, this carbonyl of a ketone, normally you might find it at 1720. But as soon as you add a conjugation by including that double bond, see, you have double bond, single bond, double bond. You have an alternating system. That is a conjugated system. As soon as you have conjugation, you're introducing resonance. And that resonance, you can draw it like this. You know, it spreads out all around these three atoms. So that's going to make that carbon-oxygen double bond weaker. And sure enough, we can see that we can find its wave number at 1680, much lower than 1720. So conjugated systems weaken the bonds, so they lower the wave number. Any questions about this one? So this is why I'm telling you that the numbers are not absolute. It really does depend on the rest of the molecule. They're both ketones. They are both ketone carbonyls, but one is conjugated, one is not. They have different wave numbers. Okay, any questions about this one here? Okay, moving on. Alcohols and phenols. Well, a phenol is simply just a benzene ring with an alcohol. So it's still an OH regardless, right? A phenol looks like this. Well, that's still just an OH right here. So in general, alcohols and phenols, they all have the OH stretch. Might look a little different, but it has the same region, the same stretch. So this one is the one that we saw earlier. At around 3350, 3300, we saw this broad, strong peak. This is very characteristic of OH. I don't know if you guys can see the yellow very well. Let me use pink. This is very characteristic of your OH right here. And that'll happen between 3200 and 3500. Sometimes a little bit more, sometimes a little bit less. It depends. And it's very broad signal. Why is it broad? Because it can hydrogen bond. Remember hydrogen bonding? You have like a sort of electric bond that gets formed between an H and an oxygen. It has to be bonded to a nitrogen. It has to be bonded to an oxygen. It has to be bonded to a fluorine, and it can make a hydrogen bond with those exact elements. Hydrogen bonding is making the spring stiffer. So you need more energy, so you're going to have a higher wave number. Make sense? And not all of the OHs are going to be hydrogen bonded at the same time. Some of them might be forming the bonds, some of them might be breaking the bonds. So you get a spread in the wave number energy of absorption, and that is why you get this distribution of absorption. You get this broad signal of the OH. Make sense? What's this over here? What's this? Around 3,000. What is this whole thing? Somebody tell me. CH stretch. That's right. That's right. Be very specific. You can't just say bonds. Sure. What kind of bonding? Is it a bending vibration? Is it a stretching vibration? Right? You have to be specific. This is a CH stretch. They give you the molecule. It's one hexanol, right? And they give you the formula so you can draw it out. If you do that, you'll see there's no double bonds. There's no triple bonds. So this is an sp3 CH stretch. And yes, you do have to say that if you know it. If you can't tell because you're not given much, you can just tell me these are CH stretches. But if you can tell, you need to be specific with what kind of CH stretching it is. So the stalactites are always there in every spectrum. Okay, what else do we have here? Well, you'll notice over here at around 1100, we have a stretch of the carbon, oxygen, hydrogen. So this one right here, the carbon-oxygen bond, polar bond, there's only one carbon-oxygen vibration. The rest of the molecule is hexane. So you see one signal that is kind of like medium strong, very sharp at around 1100. So carbon-oxygen bonds are found between 1100 and I would say maybe 1250. Carbon-oxygen bonds, single bonds. And you'll usually see them like this. You're also going to see carbon-oxygen bonds and ethers. So you need to remember these numbers. That's why I hesitate to call anything above 1000 fingerprint, because carbon-oxygen shows up at around 1100. That's not fingerprint. You can still see it. So that's why it is my own definition that anything below 1000 is considered fingerprint. So hopefully that makes sense as to why I think that. So once again, the hydrogen bonds of the OH are what spread out the signal, and OH is a very polar bond. It's also a 1 molar mass versus a 16 molar mass atom. So it's a very intense, strong signal, and that's why you see it. It's also very smooth, right? We used the word smooth earlier. It's a very smooth peak. So any questions about this one? All right, so let's look at some more. Carboxylic acids. Well, they contain alcohol, so it makes sense, right? And they also contain carbonyls. So a carboxylic acid is a compound functional group of a carbonyl and a hydroxyl. Carbonyl plus hydroxyl equals carboxylic acid, right? So you should see the signals of both groups in the IR spectrum. So for example, again, carbonyls, we usually find them at 1700 plus minus 50. General rule. So look, here's 1500. So there's 1600. Here's 1700. And look at that. There is a very strong, sharp peak at around 1710 maybe, right? That is your carbonyl. And then remember that hydroxyls, OH bonds, tend to be found in higher wave numbers. And so in this case, you get a very broad signal, just like you normally would from an alcohol. But look at this. You start at almost 2500 wave numbers and you go all the way to 3500 wave numbers. That is a spread of 1000 wave numbers right there. That's a very big, very broad signal, right? Very broad. We usually say VB, very broad signal. What are these right here? I'm going to use the color pink. What are these in the color pink? They're at 3,000. What is this? Why are they sharper? What is that? They're everywhere, remember? All molecules have them. What is this? You have an answer. It is CH stretch. Yes, exactly. These are your CH stretches. Now, in this case, we're not actually given a formula, so we don't actually know what kind of CH stretch it is. So you could just tell me this is a CH stretch right there. And you'll notice that the signal of the OH, the hydroxyl and the carboxylic acid, it's so broad, it actually like swallows up the stalactite signal. You only see the very bottom. So we actually call the whole thing, we call it a beard, like a wizard's beard is one way that we use. So I can draw like the eyes up here and, a smiling face, and you can draw like a little like wizard's hat right over here, like looks more like Santa Claus. And then, of course, this whole thing right here is the beard, right? So the wizard's beard. So if you see a spectrum and it looks like it has a very broad signal around 3,000s with the stalactites overlap so that it looks like a wizard's beard, and then you see a carbonyl at 1700, that means you have a carboxylic acid. Very characteristic, right? But you have to be able to know what an OH looks like and what a CO, what a carbonyl looks like. It's both of them, right? A common mistake people make here is they'll say, oh, this is a carboxylic acid. Wrong. This is a carbonyl. That's it. You don't know what kind of carbonyl. Or they'll look at this and they'll say, oh, look, this is a carboxylic acid. Wrong. This is a hydroxide. This is an OH only. It is the combination. It is the observation of two signals, the one from 2500 to 3500 and the one at 1710 that lead us to conclude that this is a carboxylic acid together. You cannot conclude the whole thing from just one. You have to take them both into account. You cannot call either signal carboxylic acid. That is just completely wrong. One is a carbonyl signal, one is a hydroxyl signal. So make sure you don't lose points because you have to use the very specific language to describe it. How do I learn the language? You practice. You do more spectra every day, more practice. From now on, there are gonna be spectra in your lab worksheets, and of course, they're gonna show up in your final exam as well. So it's a good idea to be practicing spectra for the rest of the semester. So yeah, it's what they look like. And again, that giant spread is just caused by the excessive hydrogen bonding that you can get from a carboxylic acid. So you get the spread that's even larger than a standard alcohol. So any more questions about this one? Okay, let's look at the next example. Ethers. An ether is a carbon-oxygen-carbon bridge. So this one is dibutyl ether. So let's draw it. Dibutyl. So we have two butyl chains. Butyl means four, and then it's an ether connecting them. So I draw two 4-carbon chains connected by an ether. So let's do it. 1, 2, 3, 4. So that gives me my 4 carbons. I have to draw the oxygen bridge, and then I have to do 4 more. So 1, 2, 3, 4. There it is, dibutyl ether. Very simple molecule. I only have carbon-hydrogen bonds. I only have carbon-oxygen bonds. So you see the spectrum looks very clean. So let's take a look. Again, we start at the high wave number. Look at the biggest wave number. I'm going to use green. What's this? It's everywhere. It's present in all spectra. What is this? The stalactites. What are they? We got someone in the chat. CH stretch. Yep, that's right. And again, be specific. You have the structure, so you can be specific. All of these are tetrahedral carbons. All of these are sp3 carbons. So these are your sp3ch stretch. You have to know that. You have to know that. What else? Well, we saw these two earlier. These are probably our CH bending. Which ones? I don't know. I just know that there's CHs on their bendings, right? I can only tell from the stretches. The bendings, there's all sorts of bending motions. And look at this one. This carbon oxygen, it's a strong peak. It almost looks like the carbonyl peak, but it is not at 1700. This is at like 1100 or so. And this is what I was trying to emphasize earlier, that carbon oxygen single bonds, they have a strong signal. It almost looks like the carbonyl signal, but it is not at 1700. If this was a carbonyl, I'm going to use pink. You would see right here at 1700, you would see a signal that looks very similar. It would look maybe something like this. But notice it's not at 1700. It's at 1100. The wave number is lower because it's a carbon-oxygen single bond. Single bonds are weaker than double bonds. Carbon-oxygen double bond is going to be a higher wave number. So that's how you can tell the difference if it's a carbonyl or just a regular carbon-oxygen bond. Don't get those two confused. That's another point of confusion here. Carbonyls are at 1700. Okay? But the carbon-oxygen will look very similar to a carbonyl. It's just at a lower wave number. So just make sure. And there's nothing else, right? It's a very simple molecule. So again, we only look at the characteristic signals and we can just make conclusions and move on to the next one. How are we doing so far? Like, is this making sense now? Like, instead of squiggly lines, are you starting to see the patterns a little bit? Yes. Alrighty. Yes. Thank you. Thank you. Yeah. More practice. This is one of those things. The more you do, the better you get. The more you do, the better you get. So let's do more. Okay. So here we have esters, right? Here's the formula. Esters are carbonyls and ethers together. So you have a carbonyl and you have an ether. That is an ester right here. This is an ester functional group. So you're going to look for the carbonyl signal and you're going to look for the carbon single bond signal. Again, we start with the highest wave number. What's over here? What's over here in the pink and the purple? What's this? I can see patterns. Yes. Yes, the patterns are the key to everything. So what's this here at around 3000, 2900? What are these? These are everywhere. Every molecule has them. sp3ch stretches. Exactly. How do you know it's sp3? Because look at your structure. They tell you that all the carbons except for the carbonyl one are tetrahedral. So they are all sp3chs. So this is sp3ch stretch right here. Look at this. Carbonyl stretching. Where is it at? I'm going to use green. Where is it at? It looks like it's at like 1750 roughly, right? 1750. That's where you would expect to find the carbonyl. It's also very strong. It's almost to the bottom, right? This is your carbonyl right here. Carbon double bond oxygen. That would be the carbonyl of your ester, right? This is my carbonyl of my ester carbonyl. And then finally, look at around 1100. 1100 is right here. So a little bit more, maybe 1200. You have your carbon oxygen single bond. That's this bond right here. And it's also polar. And also look, it has almost the same intensity as a carbonyl, but the wave number is lower. If you're expecting to see it, look for the strongest signal at around 1100. That'll usually be your carbonyl, not your carbonyl, your carbon single bond oxygen. There's also another one that's a lot weaker. So it does show up, but it's not really that apparent. Like this one right over here in the orange, that's this one. Because this is also a carbon oxygen bond, right? But this side is more polar, so this one has a higher wave number. So as long as you can point out the strongest signal in the 1100s and tell me that is a carbon oxygen ester bond, you should be fine. Look for the strongest signal at around 1100. That is most likely going to be your carbon-oxygen bond, and it's a single bond. Look at the bottom. In the bottom, we have also an ester compound, but it's aromatic. It has a ring. So remember, aromatic rings make the signals sharper. So if you look at it, it looks very pointy, very spiky. So again, let's look at 3000, at the 3000 area. What do you see here? Stalagmites. So what are these? These are your CH stretches. Every molecule has CH stretches. So make sure you can identify those right away. Notice the intensity. These are weak. The one on top is more strong, right? The intensity is weaker here because double bonds are stiffer, so it takes more energy to vibrate them. So they're not as intensely vibrating, right? It's aromatic, so look at this very sharp peak right there at around 3000. This one. This one is this one right here. This is your carbon hydrogen aromatic vibration right there. Make sense? Very unique. Notice the little hills at around, well, actually, they kind of get obscured. You can't really see them that well. So this is what I mean. Sometimes you'll see some hills, sometimes you won't. Here, it looks like they're being kind of interfered with, so you can't really see them that well. We have a carbonyl in the green right here. So again, we go to 1700 and look at that. There is your very strong carbonyl signal right there. You have an aromatic ring, so you should expect to see some very sharp carbon-carbon double bond peaks. That's going to be those right here. Carbon-carbon double bonds. And then you have an ester, so you have a carbon-oxygen single bond. Look for the next strongest signal right here at around, this one's at 1300, probably because of some sort of conjugating polarity effect that we're not sure of. So again, these numbers are general numbers. You still have to use reasoning. If you have a carbon-oxygen single bond, look for a signal that might be that signal, right? Make a guess. This one right here, that one doesn't make sense because that one's in the fingerprint region. See, it's at like 700. Ignore this one. That one doesn't make much usefulness. But look, this one here at 1300, that one is the strongest. This one at, I think that's 1100. This is the second strongest. So either one of these might be your carbon-oxygen single bond. So again, the more you practice, the better, right? I don't expect you to just know from now on forever what it looks like every single time. It really depends on the molecule. It depends on the whole environment. So any questions about any of this? And again, hopefully what you're getting out of this are the patterns, right? The peak at 1700, the stalagmites at 3000, the broad peak at 3300. You're starting to see that all of those are unique to a functional group. Okay, let's move on to the next example. Amines. Amines. Nitrogen, hydrogen is similar to oxygen, hydrogen, right? Carbon, oxygen, nitrogen are all next to each other, right? It's carbon, nitrogen, oxygen, fluorine, neon, right? So oxygen, hydrogen is very similar to nitrogen, hydrogen. They're right next to each other on the periodic table. It's going to be around the same wave number region. They're both polar. They can both hydrogen bond. It's a little less polar, so the intensity might not be as strong as an oxygen-hydrogen bond, as a hydroxyl. So again, what are these right here? I'm going to use the color green. What are these? What is this? They're at around 3000, 2900. What are these spikes? What is this whole thing? It's everywhere, right? What is this? You need to know. And you have the structures, so you can tell me what kind it is. It's an sp3ch stretch. Yep, that's right. You gotta give me that answer if you know the structure, because otherwise it's not gonna be full credit. You need to tell me that based on the structure, this is an sp3ch stretch. You have to tell me that. All right. At a higher wave number, we observe weak signals. Those signals are amines, NH bonds. Those signals are the NH bonds. And depending on how many NH bonds we have, we're going to see how many peaks we have. So for example, primary amines have two NH bonds, nitrogen, hydrogen, hydrogen, some sort of carbon. So each one of these NHs has its own peak. And so you see right here that you see two weak peaks at around the same region as an alcohol, right? 3200 to 3500. How does this look different from an alcohol? Well, I'm going to use this violet color. If this was an alcohol, it would look more like this. It would be a lot stronger and it would be a lot smoother, right? So if you see that it's weaker, it cannot be an alcohol. It could probably be an amine. How many hydrogens? That depends. If there's two peaks, you have two NH bonds. If you have only one peak, you have only one NH bond. So now you know if you have a primary amine or a secondary amine. So you need to know this as well. You can tell me, and again, if you have the structure, you can just confirm, right? There's two NHs here, so obviously there's two peaks. There's one NH here, so there's obviously only one peak. And it's always higher wave number than the stalagmites. So this is why you need to recognize the stalagmites and look at everything else in relation to them. Tertiary amines do not have NH. Tertiary amine is just nitrogen, carbon, 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 and lone pair. There is no NH here. So there is no peaks in the NH region. That's why tertiary amines do not have any bands at all. So if you have a compound that has a nitrogen-carbon bond, don't be looking for amines. Amines are only nitrogen-hydrogen bonds. If it's only carbon-nitrogen bonds, those are called amides, right? So any questions about this? So let's look at some examples for this one. Oh, I think that's all of them. So cool. This is where we basically just start going through a bunch of spectra and start seeing even more patterns. So any questions so far? All right. So let's look at the spectra here, the spectrum. What functional groups are in here? What do you see? What can you tell me from looking at this? Okay, the chat. Carboxylic acid. All right. So there is a carboxylic acid here. So now give me your evidence. Give me your evidence. Why is it a carboxylic acid? Where are the peaks? Give me wave numbers. Give me descriptions. Very broad peak from 3,500 to 3,000-ish. Okay, sure. Very broad peak. What is that one? What does that one correspond to? Wrong. It's not carboxylic acid. Carboxylic acid is made of two things. You have to be specific. Annie said OH. Right. What is it called? What is the actual name? Don't just say OH. What is it actually called? It is OH. You're right. But what is it actually called? Let's practice names. Hydroxyl. This whole signal is your hydroxyl signal. Make sense? That's why you can't say carboxylic acid. And then people are already saying in the chat that at 1700, right here, 1700, we have a very sharp, strong signal, right? This is your carbonyl signal. Very iconic, very characteristic. So if we add those up, carbonyl plus oxygen, hydrogen plus hydroxyl, right, gives me a carboxylic acid. And so remember, neither of these peaks is a carboxylic acid peak. That doesn't make sense. That doesn't make sense, right? It's either a carbonyl peak or a hydroxyl peak. So you cannot use the word carboxylic acid to describe any one peak. It is the total analysis that concludes that it is a carboxylic acid. But this has a hydroxyl signal and this has a carbonyl signal. Very specific. So any questions about this one? Well, what about these peaks over here and this one? Well, we're not provided with the structure, so this could be carbon double bond carbon. This could be just carbon hydrogen bonds. I don't know. We don't have any more information. All we can conclude for sure is that there is a carboxylic acid in this molecule. Nothing more. Okay, let's try the next example. See what we get. Yeah, you will lose points if you say carboxylic acid for any one peak. So that's why I have to be very strict with this. Like it's very specific. Alrighty. Here's the next one. What do you see? What do you see? What functional groups are present here? Again, give me numbers, give me descriptions. Okay, so hydroxyl, CH stretch, okay. Okay, perfect. Excellent. Yes, yes. Broad peak at 3,500-ish from a hydroxyl. Excellent. Yeah. It's not exactly at 35. It's a little lower than that, right? Look at the highest point and like come a little lower. It's like this is like a 34, but in general, it's broad. It starts at around 32 and it goes up to around 36, right? So this is a broad signal, strong signal. This is your hydroxyl signal. This is your OH alcohol signal, right? You can say alcohol instead of hydroxyl if that benefits as well. Just give me a name. You have to practice the language. That's why. And then at 3,000, you have the sharp peaks for sp3 carbon hydrogen stretches. Yep. We assume they're sp3s because we don't have any other structural information. So in this case, this is the only case where it is acceptable to just say CH stretch. Why? Because we have no formula and we have no actual structure of anything, right? So the only thing we know is that these are some sort of CH stretches. And that would be okay in this case because we have nothing else to go off of. Let's see. There's nothing at 1700, right? If this was a carbonyl, I would see a peak at 1700. I don't see one, so there's no carbonyls. And I just see a bunch of sharp peaks closer towards the fingerprint region. So I don't think that these are very telling. I don't know what else we can conclude without a formula. So the only thing we can say for sure is that there is an OH in this structure for certain. Any questions about this? So we don't always use all the signals. We only use the characteristic signal. Okay, let's look at the next example. What about here? What functional groups are present here? What do you see? What functional groups do you see here? So Annie said from 3,300 to 3,500, primary amine. Correct. Yes. There are two weak signals around the same area as you would expect to find the hydroxyl, but they're weaker, so they correspond to NH. So this is an NH2, right? This one is this one, this one is this one, and it's a primary amine, so there's only one nitrogen carbon bond. So yes, make sure you're specific, primary or secondary. Fernando said sharp peaks at 30,000 at 3,000-ish for CH stretch, right? Yeah, these are your CH stretches, but we don't have any structures, right? We don't know what else there is in there. So we can just say CH stretch for this one. We don't have any other evidence to show what they are. Anything else that we see here? I don't really see much else, right? This could just be bends, some CH bendings. Maybe some of these are the NH bends. We don't really know. The only thing we know for sure is that this has a primary amine. Make sense? We don't always use all the peaks. We're looking for characteristic compounds. This is why you cannot tell me the whole thing just from looking at a spectrum. The spectrum only tells me about the groups, nothing else. I'm sure there's actual analysis of spectra and physics and everything, but we don't do that here. Let's look at the next example. What's this one? What do you see? What do you see, guys? Excellent. Yes, both of them correct. Yes, yes. A secondary amine at around 3,300, 3,400, right? Let's see. It looks like it's 33-ish, 3350. Let's just call it 3350 just for compromise. You see a weak, sharp signal. It's actually at around 50, so I would actually call that medium at this point. But also look at the baseline. The baseline starts at 80. So actually, that's actually weak. It's not very far off from the baseline. So this is still a weak signal. Oh, I don't know what happened there. Okay, there we go. Let's leave it there. 3350. This is just a single NH. There's probably a carbon and a carbon here. So this is a secondary amine. What's all this over here? What's all this nonsense here? CH stretches around 3,000. Exactly. This is always there. These are your CH stretches. We don't have any structural information, so we cannot make any more claims about what they are. We just know that these are CH stretches. What about over here? Can we see anything else? Well, this is one of those interesting cases where you actually can make one more assignment. If you have a secondary amine, you have two nitrogen carbon bonds. And if you remember, it's carbon, nitrogen, oxygen, fluorine, right? Carbon oxygen is very similar to carbon nitrogen in terms of polarity, in terms of strength. So if you can find carbon oxygen bonds around 1100, you can probably find carbon nitrogen bonds around the same region, right? You look for a strongish signal. And so this peak right here, I would feel very confident assigning this a nitrogen carbon single bond right there. But this is more like intermediate, right? This is where you start thinking about the whole thing. As long as you can identify the main one, which is the amine stretch, you should be good. But again, as you start getting more practice, as you start seeing the patterns and you start integrating the principles of Gen Chem 1, then you kind of start making predictions, right? Here's another prediction you can make. If a carbonyl is at 1700-ish, well, again, carbon and oxygen, and then carbon and nitrogen are right next to each other. So you could tell me, okay, where do you think this one might be? Well, let's see. Oxygen is more electronegative than nitrogen, so this one is a more polar bond. So this one is going to be weaker. So I might expect a carbon nitrogen double bond at maybe, from 1500 to like 1600 perhaps. You see? So we can start making predictions as well once we have some references to refer to at all times. So that's how I can clearly and confidently assess that this is a nitrogen carbon bond at around 1100. Maybe I'm wrong, but we do our best. We guess. It's very reasonable. So yeah. Again, this does not give you the complete information. This is just something else you use in conjunction with everything else we've learned to identify a compound. Any more questions about this? Okay, more examples. Unknown number one. What do you see here? OH broad stretch at 3300. Yep. And I don't know if you typed that up earlier or not, but CH stretches around 3000. That's right. That's right. So again, at around 3000, 2900, you have the stalagmites. These are just your CH stretches, always present. And then here you have a broad, strong signal between 32 and 35 hydroxyl. Alcohol for sure. Very smooth, right? And then what else? I don't know. I mean, this is probably some CH bend over here. Can't really tell for sure. This one looks similar to a carbon oxygen, but I don't know what else is in there, right? I don't know if this is connected like this, COH. That might be this one. But what if it's not connected to a carbon? What if it's connected to a nitrogen or to something else? We don't know. So, question mark, right? All we know for sure is we have an alcohol. Is this making sense? Okay, next example. Let's see what else we got. Ooh, interesting one. So what's here? What functional groups are present or maybe not present? Hmm. What do you guys see here? Ooh, we got two conflicting hypotheses here. We're saying it's probably an sp2ch stretch or a secondary amine. Which of the two is it? Well, let's take a look. A secondary amine is a weak signal, right? And usually it's found between 3200 and 3400. So if we look at this whole region, we see that it's just very slightly out of range of where we might expect an amine. And yes, the peak is very sharp, right? And it's also very slightly to the left of all of the stalagmites. So this whole region in general is a CH region. So the fact that there's one peak in the CH region that is sharp, a little bit higher wave number, that tells me this is a stronger bond. So yes, this one would be for sure. I don't know why sometimes it doesn't clear up. Anyway, this one here is for sure an sp2ch stretch. All right. And also, there is a, yeah, see, I can't erase it. Not sure why. There is a very sharp peak also in the stalagmites. I'm going to use the color pink for this one. That peak right there, we saw it earlier. Something makes a whole spectrum very sharp. What is that? What makes the spectrum sharper? An aromatic ring. So this is your aromatic carbon hydrogen stretch, right? You could have like a ring and you have that H right there. And this whole thing is just like the rest of the ring right there. So yeah, this is your aromatic carbon hydrogen stretch. This whole region in general are just carbon hydrogen stretches. And also notice you have like the little band of hills up here, the Oberbands. So you have Oberbands right there. You also have a peak at around 1600 that is very sharp. This is your carbon-carbon double bond peak. Not very strong, but very sharp. And this one is probably some sort of bend, right? Some sort of carbon-carbon bend. I don't really know. It's hard to prove. Can't really tell. All we know is we have this sp2ch stretch. We have this aromatic carbon-hydrogen very sharp peak. And we have this sharp but weak carbon-carbon double bond with right where the overbands are located. And there's nothing else, right? That's another clue. There is no carbonyl at 1700, right? There's nothing here at 1700, no really strong sharp peak. There is no alcohol at 34, 35. There is no amines because it would look a lot like, more not too sharp, a little less, a little more blunt, I should say. So yeah, and again, I can see why you're making these conclusions. The best thing to do is to keep looking at examples. You'll eventually see what they look like. You just recognize it by sight. You can see what it is. So we do have more examples. Let's keep working through them. What about this one? What do we have here? Carbonyl peak at 1700. Yes, excellent. There is a carbonyl peak at 1700, right? So there's 15, there's 16, there's 17. Not exactly at 17, but it fits the plus minus rule. It's very sharp, very strong. So this is definitely a carbonyl peak. That's where you would expect to find it, right? Do we see anything else? Is this a carboxylic acid carbonyl? Do we see a wizard's beard anywhere? Well, we do see the CH stretches right here, right? These are CH stretches. No carboxylic acid. Nope. Ooh, Annie is saying that there's an aldehyde stretch at 2900. Let's see, the 2900. You mean this one or this one, right? This is in fact an aldehyde stretch right here. It's both of them. They have like one of them is like in and out, and the other one is like a little like left, right, or it has some sort of other motion with the carbonyl. But it does produce two peaks. In general, if you pick one or the other and you tell me it's an aldehyde, I would consider that an acceptable answer. So this is definitely an aldehyde carbonyl because there is no wizard's beard, so it cannot be a carboxylic acid. There is something at 1100, so it could be an ester, but it's very sharp. It's a very sharp peak right there. This is not characteristic of an ester carbon oxygen bond. So I would say that this is not a CO. This is not a CO. So it's not an ester. It's not a carboxylic acid. It's not an amide, or you would have like an amine, like you would have like one or two right there. So it's not that either. So it's either just a ketone or it's an aldehyde. Well, you do have this signal right there that it's a little lower in wave number. And remember, that is just the carbon hydrogen stretch of an aldehyde carbonyl. So that is how you can point out what aldehydes are compared to other things. So yes, Annie, you are correct. This is definitely an aldehyde carbonyl. So if you draw the whole functional group, you would just draw it like this. What else is there? We don't know. We're not given a structure and we're not given a formula. We cannot make any more conclusions. All right. And again, just more practice. That's really it. What's the shortcut? Do it again. Do it again. Do it again. Keep doing it. Okay. Let's look at the next one. What's this one here? Fairly clean spectrum. I'm gonna go grab some water real quick while you guys think about it. Give me like 1 quick minute. Okay, so what did we come up with? What's here? What is the spectrum? CH stretches, right? Where? Remember, you have to give me numbers too. You can't just give me like CH stretches. As far as I know, you're just naming things. Exactly, like 3,000, a little less than 3,000, but if you say 3,000-ish, I get what you mean. So, I mean, that's fine. 28 to 3,000, these are your CH stretches. Are they SP2, SP3? Hard to say without a formula. So all we can say is that it's some sort of CH stretch. What else do we see? I think I misspelled stretch. Stretch. There you go. I know some people might be like, oh, you misspelled a word. What else is in here? Yeah, it might be aromatic, but remember, if we saw aromatic, one of these peaks, not only would the intensity be smaller, like these peaks might just be up here, but one of them specifically would be very sharp. CH2 bending at 1500. Yeah, this is some sort of bend. This is some sort of CH bend. Which one? Quién sabe? I have no idea, right? We just know it's some sort of CH bend. Is there anything else here? Are there carbonyls? Are there alcohols? Are there amines? Are there ester, carbon, oxygen? Like, is there anything else in this spectrum? So it must be what? This is just a what? What kind of compound is this? Exactly. This is just an alkane. If we had a formula, we could confirm. But just based on the absence of anything else, we can conclude safely that this is an alkane. We don't have anything else to go off of. We need a formula or a structure. Otherwise, this is all we can say. Maybe we're wrong, but with the given evidence, that's all we have. Okay, let's look at the next one. What's this one? What do you see here? OH stretch at 3300. Primary amine at 3400. So it might be an OH, it might be an amine. Which is it? Which is it? How can we tell what it is? Exactly. The intensity would be stronger and it would be smoother if it was an OH. So if it was an OH, it would look just like this. It would be roughly in the same region, but it would look a lot more smooth. Something like that. A lot more strong. And yeah, he's got the two peaks for the primary amine. Each one of these peaks corresponds to an NH. So this is NH2. NH, NH. That's why you have the two peaks right there. Notice the signal is in the same region as alcohol, but it's not smooth. It's also weaker, right? Medium, I would say, based on this. But again, look at the background. The background here starts at 80. So actually still weak, right? You do have to look at those things. But regardless, the peaks are where they should be. Yes, we have our CH stretches around 3,000. Yep, a little less than 3,000. What else do we have? I mean, I don't know. Everything else. This could be bends. These could be CH bends. 1,400. Maybe. I mean, this could be a CN right there, right? It could. Maybe at 1,100, but there's not a lot more peaks. So whatever this compound is, that CN stretch is not very apparent. So maybe it is this one, right? If you told me it's this one, I wouldn't hold it against you. But all we can safely conclude for sure is we have an NH2. Nothing more. Without more information, right? You cannot use this to get a complete picture. This is always a partial picture. Okay? Next example. Sometimes you're gonna see spectra that look terrible. Like whoever did this hasn't cleaned their instrument, hasn't calibrated it in a while. This is like when sometimes we have a TLC and the spots are a little bit too large. But remember, we can still get information out of it. So even though this spectra might not be the best looking spectra because the baseline starts at like 60%, my goodness, they gotta clean their instrument. This is still enough information. So what do we see here? I have a question. It says, for the quiz, would it be like these unknowns where we identify functional groups, or would you give a formula? Yes, I will always give you either a structure or a formula. I'm not just going to give you this. And if I give you just the spectra, you might just have to tell me the functional groups you see. But I'm not going to tell you like, give me the molar mass of this compound based on this formula. Wow, that's impossible. No. I might ask you to fill in and complete the molecule. Like, here's partial structure of the molecule. Look at the spectra and tell me what other things go in this molecule, right? And you'll have to actually draw the molecule at the end. But you don't get nothing. You get something always. Okay, Fernando said OH broad stretch from 35 to 30 belonging to a carboxylic acid probably. What? Okay, so you said OH broad stretch to a carboxylic acid. Okay, that was me. That was me looking for a fight. You're right. You did say OH between 28, 33. Perfect. Yes. The wizard's beard, right? There's the wizard, and there's the hat of the wizard, and this whole thing is the beard. Looks more like Santa Claus now, actually. But very broad, roughly around 1,000 wave numbers. So this is a hydroxyl, probably of a carboxylic acid. How do you confirm? Well, Maria said that at 1,700, there is a carbonyl. And yep, there's a very strong signal at almost exactly 1,700. You see there's two peaks, but that's because, again, this is just a terrible spectra. You got to stick to what you know. I know that carbonyls are at roughly 1,700. it looks like I have a hydroxyl from a carboxylic acid, so this definitely confirms that I have a carbonyl and a hydroxyl, which means I have a carboxylic acid. What else? What else can we say? I don't know, man. Like, could this be something? Could this be a carbon single bond oxygen? Probably, but I mean, all we know is we have a carboxylic acid. So hopefully this makes a lot more sense now. Hopefully when you guys see these spectra, you're not just seeing a bunch of squiggly lines anymore. You're not panicking from all the peaks. We only look for very specific peaks, nothing much more. Okay. So you're going to be given something on the post-lab quiz that looks like this. I'm going to give you an actual paper that has the functional groups and where you usually find them and things like that. So just remind me to pass that out. I will print it out next week and give it to you guys. And look at the language, right? Strong, broad, medium, strong, medium, blah, blah, blah. It gives you the wave numbers. It gives you the types. It gives you roughly where you can find them. And again, this is not absolute. There's always a few little exceptions where they're a little bit out of range, but for the most part, we can predict most of them within these regions. So before we finish, I do want to show you one last thing. This is how you can get a lot more practice. So I'm going to go back to the websites. There is one more website. This is the Japanese spectral database for organic compounds. Right here. I will also post a link for it. It's just SDBS, Spectral Database for Organic Compounds. You're going to go to the website. You're going to click I agree. And right here, you'll see that you can search up the molecules. I think I'm zoomed in a little. Yeah. Okay. You can search up the molecule. So for example, let's do acetone. So this is how you will get more practice with IR spectra. I want you guys to go to this website and type up just molecules. Look up ethanol, look up ethane, look up ethene, look how they're different, look how they're the same, look up carboxylic acid compounds, right? So let's look at acetone and click search. You see, I'm gonna get all these results. The top one is the one I want, just regular acetone. Right here it says IR. It says Y. That means yes, there is an IR spectrum available. You're gonna go ahead and click it. There's your IR spectrum for your acetone. So use this to practice. So for example, I know that I have right here a carbonyl. I know carbonyls are at 1700. So let's go to 1700, 15, 16, 17. Look at that. This has to be my carbonyl peak right there. And if you go to this table down here at the bottom left, this table of numbers, you can actually tell me exactly where the value is. So you look for the highest absorption, right? The lowest transmittance. Look at this, the number 4 that has the lowest transmittance, 1715. So this is a carbonyl at 1715 wave numbers or inverse centimeters, right? We also have CH3, so we have our CH3 stretches right there. Doesn't seem like anything else. These are probably bending stuff, yada, yada. So again, this gives you real examples. The examples we gave you in the presentation, that's obviously designed to be easy to read, clear, straightforward. Sometimes they're not very clear. Sometimes they're not very straightforward. Sometimes the molecule changes between one molecule and another in the same solution, right? So sometimes you get different things happening. So for the post-lab quiz, I'm going to use this spectral database to find some spectra of common compounds, and I will give you the spectra. The formula will be there, the table will be there, and you will have to tell me what are the peaks. You have to assign the peaks, which ones correspond to which. Okay? So that's what you can expect for the post-lab quiz. So let's look at another one. Can somebody give me a molecule? Please suggest something for me to search. Don't suggest drugs, because you can't look up the compounds of drugs here, like illicit drugs. So give me something that is an everyday chemical, something that we use, something that we can see. Citric acid. Perfect. That's a good suggestion. Let's look up citric acid. Citric acid is a carboxylic acid, so we should expect to see some sort of beard. Let's see if that's true. All right, here it is. Third result, citric acid. IR, yes. Also, you can use this website next semester because look, you also have NMR spectra. And next semester, you're going to learn NMR. So you can use the same website. So that's the benefit you get knowing about these things. Alrighty. So citric acid, there it is. And look at that. We have a wizard's beard because citric acid contains a carboxylic acid, right? And you can see it right there. Let me annotate it. I'm going to draw it with red. Here is, there's two actually. Look, I have one carboxylic acid and I have two carboxylic acids. And sure enough, over here between 2500 and 3500, I have a very broad signal. And this is my OH, my hydroxyl for my carboxylic acid. I have two carboxylic acids, so I have two carbonyls. And look, at 1700, I actually have two peaks. This is one and this is two. Both of these are carbonyl peaks. They're in slightly different environments, so their wave numbers are slightly different. And actually, I have three carbonyls. Oh, wait, no, I have three I have three carboxylic acids. Oh my goodness, sorry, I did not see that. Yeah, so I mean that's why you get this broadening of this carbonyl signal there, right? We find it where we expected, but it doesn't look like usual because the molecule itself is different. This is what we mean by fingerprints. The molecule has a unique signature. And obviously, if you were to just look at this without the structure, you couldn't tell me that there's multiple carbonyls here. There's no way to know that. This could be interference. This could be bad preparation. The baseline is not very like 100, right? The baseline is at like 95, almost 90. So, I mean, make sure that you can only make conclusions when you have the data to back up your conclusions, right? So here I might ask you, point out the carbonyls and point out the hydroxyls. Well, here's a hydroxyl. Obviously, it's being overshadowed by whatever this is. I think it might be this one. I'm not really sure. Hard to say. But since we don't know for sure, then, we can't make any more claims. That one might be a sp2, but I don't see any sp2 carbon hydrogen stretches here. So all we can claim, even with the structure, with our knowledge that we just learned, is that there is a carboxylic acid in here. Let's do one more. One more suggestion, please. This was a good one. Thank you. I'm glad you suggested this one. One more. Let's do one more compound. One more compound, please. Surely you must have a favorite compound. Well, since no one's suggesting anything, oh, here it is. Cyclohexane. Yeah, of course it's possible. Why not? Let's look it up. Cyclohexane. All right, so there it is. First result, cyclohexane. Well, cyclohexane is just a ring of alkanes, right? So we should only see alkane CH stretches. And there it is. Look at that. All we see are CH stretches. Now, maybe someone might get excited and say, oh, look at this one. That looks like a carbonyl. Well, is there a carbonyl in the actual structure that is given to you? Do you see a carbon double bonded oxygen in there? You don't. So why would you say there's a carbonyl when you don't even have it in your structure? This is surprisingly a very common mistake. I see this a lot. I think people kind of panic and they start guessing, oh, carbonyl, carbonyl. Like you start saying carbonyl for everything. Um, Carbonyls are only at 1700. If you were to take 2 seconds and look at your x-axis, you would see that this is at 1400. If this was a carbonyl, it would be over here, and it would be a signal that looks more like this, right? So be careful. Remember, we look at wave numbers, we look at intensities, and we look at shapes, okay? Don't just start saying carbonyl out of nowhere just because you don't know or you're trying to guess. Like you will get it wrong, right? It's better to take some time and guess. What's over here? What's over here at the 3000s, at the 2900, 2800? What's this? What's all this stuff? What is this? CH stretches. Okay, and now you have a structure, so you can tell me what kind of CH stretch they are. What are they? What kind of CH stretches? That's right, sp3CH stretches. You see, we can only stretches. There you go. We can only do that when we actually have something else to go off of. Otherwise, we don't know for sure. And so this is probably a carbon-hydrogen band. I'm sure there's some sort of vibrations associating with like the chair conformations, if you guys have already done that in lecture. But as far as we're concerned, this is just a basic alkane. To give you some contrast, there was another compound suggested, but let's do cyclohexanol, right? Exactly the same thing. We're just adding an OH. Cyclohexanol. What would that look like? So again, we go back to the search, cyclohexanol, and then we search. And there it is, first result, IR. And look at that. It looks pretty similar, but not exactly the same. There's options down here on the left. You can click CCl4 or liquid film. Try to do everything with liquid film, but if there's no more, you might just have to deal with what you're given, right? So let's go to liquid film. Here it is, much better. Okay, so there's more signals. Do you see the OH signal? Where is the OH signal? Give me some range. Give me some numbers. 32 to 35, 3350. That's right. That's right. So basically anywhere from here to here, you see this very smooth, broad OH signal. These are your sp3 CH stretches. This right here, it's not a carbonyl because it's below 1500, right? So we don't know what that is. This could just be a carbon-hydrogen band. And look, now we know right here we have a carbon-oxygen single bond. So now I can actually say that right here is my carbon-oxygen single bond. What else? I'm sure there's more stuff in there, but for sure, we can make those distinctions. So again, this is the spectral database for organic compounds. I will post this on the announcements. Are there any questions so far? Anything? So yeah, please use this website to practice. Just Google random compounds, practice your nomenclature. Ethane, methane, ethanol, methanol, butanol, right? Look at the differences. See how the spectra changes. This is how we came up with the principles as chemists. And that is it. So thank you very much for your attention. This concludes our IR lecture. Are there any questions before I finish recording? Well, I got some meme in here. Is this a peak I can assign? Yes, exactly. It's kind of hard. It's kind of small to read. I can't really read the meme, but yes. So for next week, once again, we are gonna do a pre-lab quiz for lab 5, pre-lab procedures for lab 5. We are beginning lab 5. I believe it's fractional distillation or distillation in general. Double check in the course packet. The worksheet for this lab is in the course packet number 4. That will be due 2 weeks from now. The post-lab quiz is 2 weeks from now. So you have 2 weeks to let this settle in your brain, work through the module 4, ask me questions, go on the spectral database, go on CHEM223A, check it out. But other than that, I'll stick around for a few more minutes if you have any more questions, but this ends our IR lecture. Thank you for attending. I will see you next week in person. Have a good weekend, and I hope you have a good Sunday, a good Saturday, Yeah. So thank you.